afternoon, everyone. I hope you are all there, and welcome back to this webinar series of the Attochem network. Hope you all enjoy some time off during the summer. And now we are back to these seminars by the hand of a remarkable scientist, Professor Nirit Dudovich. Although all of you know her, let me just introduce her and her career with a few words. Professor Dudovich obtained her PhD in 2004, working on quantum coherent control in nonlinear optics. The same year, she moved to Canada as a postdoctoral fellow in the group of Paul Korkum. In 2007, she joined the Weizmann Institute of Science in Israel, where she established her lab for attosecond science. Nowadays, she is a full professor there in the Department of Physics of Complex Systems in the Weizmann Institute. Along her career, Professor Dudovich has received several awards, like the UPAC Young Scientist Prize in 2012 or the Greer Prize for Excellence in Scientific Research in 2013, because of her work on the generation of ultrashort pulses to probe fast processes in atoms and molecules with attosecond resolution. We will hear about this work today with her talk entitled Attosecond Interferometry. And before I give the floor to our speaker, I would like to remind you all that during the presentation, you can write down your questions or comments in the platform in the Q&A section. So please don't wait until the end. You can be writing it during the talk. And then once Nirit is finished, I will post all the questions for her. And with that, that's all. Nirit, the floor is yours.
Thank you very much, Alicia. Let me share my presentation. Alicia, can you see it well?
Yeah, that's great.
Perfect. Go ahead.
Thank you very much, Alicia, for this wonderful introduction. And I would like to thank you for inviting me to give this webinar. It's a great pleasure, although I would like to meet you all in person. In my talk, I will describe basic schemes in attosecond interferometry, and then I will show how these schemes enable us to resolve, I think, one of the main challenges in attosecond science, and this is the phase information. And then I will continue showing how phase information provides us with direct insight into some of the most fundamental and ultra-fast phenomena in nature. Before starting, I would like to thank by acknowledging my wonderful group at the Weizmann Institute. Both current and former students worked extremely hard over many years to produce the results that I will show today. I would also like to take the opportunity and thank wonderful collaboration we have for many, many years with the Max Born Institute in Berlin, Bordeaux University, and the Politecnico in Milan. Attosecond science led to a true revolution in our ability to capture extremely fast phenomena in nature. And indeed, over the past 2 decades, attosecond spectroscopy enables scientists to reveal for the first time a large variety of different phenomena, from the very basic moment of photo-ionization, and then to the ability to visualize how an electronic wave packet tunnels through an atomic or molecular barrier, all the way to charge migration in complex biological molecules, and in recent years, to ultra-fast phenomena in condensed matter systems. And these are just really few examples out of a large variety of mechanisms which all share one common property. They all evolve within a small fraction of a single optical cycle. Experimentally, we do not have a direct access into these phenomena. Instead, what we can resolve is their signature. Their signature maps into the appearance of high orders, harmonic, or the measurement of energetic photoelectrons. And one of the main challenges in attosecond science is the following question. Can I take those observables, harmonics or photoelectrons, and then trace them back into their dynamical origin? The challenge itself is imposed by the measurement. In the lab, we can perform intensity-only measurement while the phase information is naturally lost. And therefore, if I want to take those observables and then trace them back from frequency domain into the time domain, then we have to find a way to somehow resolve the missing part of the puzzle, and this would be the phase information. As in many other branches in physics, phase information can be directly retrieved with interferometry. So how do we perform interferometric measurement with attosecond precision? At this point, let me go into the origin of this field, the moment at which attosecond pulses are generated in our lab. We all know that we can describe this strong field light-matter interaction that leads to attosecond pulse production using a very simple, almost classical picture. So here's a picture we are all familiar with. It was introduced almost 3 decades ago, known as the 3-step mechanism. Let me shortly repeat it. So here is one optical cycle. At the peak of the optical cycle, a strong laser field suppresses the Coulomb barrier and an electron can tunnel out. Once the electron is free, it is accelerated by the strong laser field, accumulate high kinetic energy before eventually it may recollide with the parent ion. Recollision leads to the emission of optical radiation in the XUV or X-ray regime with attosecond duration. And the beauty of this mechanism is that it can be described by a set of semi-classical trajectories. Each one of them has a well-defined moment of birth within the optical cycle, moment of return, and each one of them is mapped eventually to a specific harmonic order. But the most important, in my opinion, aspect of this mechanism is its coherent property. It lies in its ability to preserve phase information. In this process, we directly transfer the coherence of a strong laser field into the coherence of an electronic wave function that interacts with the field on a subcycle timescale, and then upon recollision back into the coherent properties of the emitted attosecond pulses. So when we look at the harmonic spectrum on our detector, we realize that it contains rich information regarding the subcycle evolution of electronic wave function. However, if I want to take those harmonics and again trace them back into the time domain, we have to find a way to either build or induce an interferometer. An interferometer that will provide us with the full information regarding not only amplitude but phase as well. And in my talk, I will describe different schemes for attosecond interferometry, and I will show how these schemes enable us to obtain a very sensitive and unique insight into ultrafast phenomena in nature. And let me start with one of the most simple mechanisms we can think of, the removal of a single electron from a neutral system, photoionization. Photoionization projects the quantum state of matter into free electrons that we can directly measure, and this is why it's such a, I think, basic and fundamental measurement tool. And once we enter the attosecond regime, then there are very interesting questions that we can address and could not have been addressed before. For example, how long does it take for an electron to photoionize? Are there any delays associated with the photoionization mechanism? How would the bound state of the wave function eventually influence the ionization dynamics, and would the other electrons in the system eventually leave their impact on the photoionization process? And indeed, over the past decades, there have been a large number of beautiful experimental and theoretical studies showing the ability to fully resolve the origin of photoionization. And at this point, let me go back to the very simple 3-step mechanism that we are all familiar with. We understand it's an extremely accurate process, so it provides us naturally with attosecond precision, and it preserves coherence. So can I apply this mechanism in order to probe, as a very specialized probe of photoionization? Naively, the answer is no, since this is a strong field mechanism which doesn't provide the natural condition to resolve weak field single photon transition. However, we realize that if we look at the last step here, then photoionization is already there. It's there in its inverse mechanism of photo-recombination. We can visualize the photo-recombination as an inverse mechanism of photoionization. So the two processes are almost identical. They are described by the same transition dipole moments, and they encode the same dynamical properties. However, there is one important difference between the two. In photoionization, we generate electrons. We do not have a direct access into the phase of those electrons. Instead, we can perform a nonlinear mechanism, such as in the well-established scheme of Rabbit, interfere two spectral component and resolve not the phase, but the phase derivative. And this phase derivative represents delay in photoionization. Once we switch from electrons to photons, then the problems become much more natural because we know how to resolve the phase of an optical radiation. All we need is a proper interferometer. So schematically, the idea sounds very simple. We all know how to build such interferometers. However, maintaining the stability and the accuracy of an optical interferometer with attosecond resolution is a non-trivial task, and indeed it took us several years to achieve that. So here is a schematic description of the attosecond interferometer that we have constructed in my lab. We start with the easy part of the story. We focus intense laser field into some gas cell, and we generate a train of attosecond pulses. Now, the two fields, the attosecond XUV field and the strong IR field, co-propagate. They're reflected from two segment mirrors, which can manipulate the relative delay, and then focus back into a second gas source, generating a secondary source for attosecond pulses. Eventually, the two attosecond pulses interfere in our spectrometer, since we cannot distinguish between them. And if we're able to achieve attosecond accuracy and stability, then controlling the relative delay between the first and the second source would lead to the following result, which made us extremely, extremely happy. So in the following movie, we scan the two sources, delay, and this is what we observe. We observe simple beating, where each frequency component beats according to its fundamental frequency. So here are the beating of the 17th harmonic, and then as we go to higher and higher frequency, the beating becomes faster and faster. So with those results, we were extremely happy because we realized that now we have a direct access into the phase information of each individual harmonic order. All we need is a proper coherent reference frame. So for example, we can choose as a reference frame helium atom, and once we generate harmonics from helium, that will provide us with a relatively flat spectral phase response. And now we can interfere this reference system with any system we wish. And we started with the most simple interference between helium and neon, looking at the interference between two photo-recombination events, which represents the interference between two photoionization events. And here is the phase that we measured. So here is phase as a function of harmonic order. And we see that this phase is rather flat. It doesn't change much, and therefore there are no delays here. A Rabbit experiment would not be able to observe any derivatives. However, the phase itself is different than zero, and quite accurately, it is centered around pi/2. And this pi/2 truly reflect the different symmetries between the two atomic species. It reflects the interference between the S and the P, the S state of helium and the P state of neon. And then we can take one step further and look at slightly more complex interference, for example, between neon and argon. And here again is the phase as a function of energy. We see that this phase changes more rapidly, so there are definitely some delays here. And around this energy regime, we observe the very well-known feature of the Cooper minima associated with the argon spectrum. So attosecond XUV interferometry enable us to fully reconstruct the entire coherent properties of photo-recombination, which represents the photoionization event. In the following step, let's go all the way from weak field single photon transition into the completely other extreme, looking at field-induced tunneling. So tunneling is one of the most basic quantum mechanical phenomena. And again, as we achieve attosecond precision, we can ask ourselves many basic questions. Some of them are still hotly debated and are controversial. For example, can we measure any time delays associated with the tunneling? Can we resolve the moment at which the electron is born? And let me raise here several questions, which I will address later on. Can we follow the evolution of the tunneling barrier during the optical cycle? And then we can go one step further and ask, can we probe the electronic wave function as it propagates under the tunneling barrier in the classically forbidden region? Field-induced tunneling is also one of the most basic strong field phenomena. It serves as a starting point of almost all attosecond scale experiment. It's also one of the fastest phenomena we can think of. Intuitively, we understand that here at the peak of the laser cycle, the strong laser field suppresses the Coulomb barrier, and here tunneling probability is relatively high. However, a few hundreds of attoseconds later, the barrier lifts up and tunneling probability drops to 0. So the entire mechanism must evolve during a small fraction of an optical cycle. And indeed, about a decade ago, we have performed an experiment in helium atoms and resolve the window at which tunneling evolved. In this case, it was about 200 of attosecond, close to the peak of an optical cycle. And now let's ask ourselves the following question. We know that this barrier evolves in time. It evolved quite quickly in time. Can we watch the variation of the barrier? In order to do so, we need an additional knob that will tweak the tunneling conditions. And we can achieve such a knob if we add a weak second harmonic field on top of the strong fundamental field. Now, this field can be orders of magnitude weaker compared to the strong fundamental field, so it doesn't change the tunneling mechanism, it just adds a tiny, tiny perturbation. So if the two fields are in phase, for example, the barrier will be slightly suppressed, and if the two fields are out of phase, then the barrier will be slightly enhanced. So as we change the two-color delay, eventually what we do is we tweak the tunneling barrier. We slightly increase it or slightly enhance it. As a result, we modulate the instantaneous tunneling probability and therefore the signal of the emitted harmonics. However, such modification changes as we go from one harmonic to the other. And this is really the crucial part in this story. Each harmonic will be modulated slightly differently, where the modulation contrast is dictated by the moment at which each trajectory is born. For example, if an electron is born at the peak of an optical cycle where the barrier is strongly suppressed, then tiny perturbation doesn't do much, leading to low contrast oscillation. However, if the electron is born later within the cycle, where the barrier is already lifted up, then any tiny perturbation can have a dramatic effect, which means that different harmonic will respond slightly differently, representing the instantaneous thickness of the barrier at the moment of tunneling. So now we can go one harmonic by the other, and for each harmonic, fully reconstruct or trace back the instantaneous thickness of the barrier and therefore the instantaneous ionization probability. So here are the results of this experiment. Here is a schematic description of the phenomena we'll look at. We zoom into a window of about 100 of attosecond. Within this window, the barrier slightly lifts up. Okay, you can hardly see it. However, this tiny change leads to a dramatic fall in the instantaneous tunneling probability, changing by about 2 orders of magnitude. So far, we have applied this weak perturbation and followed the evolution of the barrier. However, we had a simplified picture in mind where the electron tunneled through a statically or semi-stationary barrier, where the barrier itself was dictated by the instantaneous value of the laser field. However, in most experimental conditions, this is far from being true. The barrier itself, in fact, oscillates very fast, and the electron, as it tunnels out, experiences the oscillation of the field in a mechanism known as non-adiabatic tunneling, and this mechanism is parameterized by the well-known Keldysh parameter. Once the Keldysh parameter approaches 1, as in our experiment, we cannot ignore the evolution of the barrier, and therefore the electron tunnels not through a static barrier, but through a rapidly oscillating one. As a result, the electron is excited under the tunneling barrier. It accumulates some energy, and eventually it is born with some initial energy closer compared to the stationary case to the origin. And such excitation is also accompanied by a phase shift that the electron accumulates, and this phase shift really encodes all the information we need to know regarding the sub-barrier evolution. Okay, so in the previous experiment, we have applied a weak perturbation, and we have seen that this weak perturbation modulates the instantaneous ionization probability. We modulated the amplitude. However, now we realize that such perturbation has quite substantial influence not only on the amplitude, but on the phase at which the electron is born with. For example, let's now change the two-color delay such that now the peak overlaps with the zero crossing of the perturbative field. In this case, the barrier itself is not modified. However, we do influence its temporal gradient. Here we increase the oscillation rate of the barrier, and as a result, we induce a maximal phase shift. So now scanning the two-color delay would lead to modulations of the ionization phase as well. Oscillations in the phase at which the electron is born with, simply because we have modulated the excitation under the barrier. So how do we resolve this phase? Let's bring at this point the scheme that I've described at the beginning of my talk, attosecond interferometry. If I now integrate these two experimental schemes, sub-cycle manipulation together with XUV interferometer, then we're able to fully reconstruct the entire coherent properties encoded in the harmonic spectrum. So this is a two-dimensional and very, very challenging experiment. Along one axis, we tweak the barrier. We can slightly enhance it, slightly suppress it. Along the other axis, we perform an interferometric measurement and resolve the phase. And now for a given position of the barrier, we can extract a certain phase. But as we scan the two-color delay, we change the barrier, we see clear oscillations as we have seen before. But if we take a closer look, we see that not only the signal, but the phase changes as well. And such phase variation are a clear signature that the electron must be excited under the tunneling barrier, and it fills the oscillating barrier. So with this experiment, we are able now to take this information and trace back, reconstructing the phase of the electron at the exit of the tunneling barrier. And we conclude that indeed it is different than zero. And here is the phase as a function of harmonic order or ionization time. And we can visualize this phase shift also as a shift of the exit point towards the origin. So far, we have looked at two different regimes for ionization, the weak field and the strong field, but both experiments were performed with very simple atomic systems. In the next step, let's go one step forward from atoms into molecules. And here we realize that field-induced tunneling serves not only as an extremely sensitive temporal probe, but also as a very precise spatial one. When an electron tunnels through a molecular orbital, it projects the outer part of the orbital into the structure of the ionized electronic wave function which is ionized. And an interesting case to consider is tunneling along a nodal plane. This nodal plane will be directly mapped into a nodal plane in the ionized electronic wave function, which is naturally followed by very rapid phase variation, encoding the symmetry of this orbital. Now, we already know that any phase information in this mechanism can be eventually retrieved by looking at the phase of the emitted harmonics. However, the question is, how do I take two tunneling events and interfere them together? Ideally, we would like to induce the following kind of optimal interferometer. I would like to take two tunneling events evolving along two different directions, and then find some clever way that will enable me to interfere them. If I can interfere them, I can trace back their phase and then trace back the symmetry and the structure of the orbital. Well, unfortunately, I cannot directly perform such an experiment. However, we can mimic. We can design a very similar experiment by shaping electron trajectories. In the following experiment, we superimpose the strong fundamental field with the second harmonic orthogonally polarized, and such combination enable us to really engineer very, very accurately the path of free electrons. For example, we can define the angle of ionization and angle of return, and we perform such engineering along the positive of cycle, and then the same engineering, just mirror image, along the negative of cycle. Eventually, the two contributions add up coherently in the harmonic spectrum, and they interfere. So what we have here is again an interferometer. It's a very different interferometer. It's a subcycle interferometer, which is really sensitive to the spatial properties of the interaction. This interferometer has two arms representing the two electron trajectories, which are mirror image. If we perform this experiment with an atomic system or any other isotropic system, then it's a boring interferometer simply because it is balanced. However, once we go from isotropic system into, for example, ion molecules, then the experiment becomes interesting because now we consider two very different events. For example, if I focus on tunneling, then here tunneling evolve in 90 degrees with the molecular axis, while here tunneling evolve at almost 0 degrees with the molecular axis. So we can envision this interferometer as a two-arm interference where electron evolve in 90 or 0 degree or any other degree that we engineer it, encoding the relative phase information provided by those two tunneling events. So in the lab, we performed this experiment with a variety of molecular systems. Here I would show one result obtained from CO2 molecules. Now we perform this measurement while we scan the alignment angle of the molecule. And for each angle, we can extract both amplitude and phase. So here is the amplitude as a function of alignment angle, and we observe the well-known nodal plane of the home orbital in CO2, followed by very rapid phase variation, again, across this nodal plane. So we were extremely happy with those results because we have shown here that by inducing an internal interferometer, which is rather different than the external one we have described before, we are sensitive to the phase encoded by the tunneling event, and therefore we can trace back the symmetry and the structure of molecular orbitals. Towards the end of my talk, I would like to focus on a recent and exciting research direction in attosecond science, looking at ultrafast phenomena in condensed matter system. Strong field light matter interaction in solids, I think, really define a new and very promising field of research, where many of the phenomena have never been resolved. When the field strength approaches several volt per angstrom, it becomes comparable to the bandgap energy over one lattice site. So in this regime, the band structure itself can be dramatically modified in a reversible manner during less than one optical cycle. So in this regime, for example, different groups in our community have resolved how an insulator becomes a conductor or how transparent material becomes an absorber during less than one optical cycle. And one of the most important, I think, discoveries was the observation that harmonics can be directly produced from a solid state target. And that really opened a new branch in harmonic spectroscopy. There are different mechanisms to describe the generation process. Let me focus on one mechanism which is very similar to the one we're familiar with in the gas phase case. Here at the strong laser field, an electron can tunnel ionize from the valence into the conduction band, initiating an electron hole wave packet. This wave packet propagates within the band structure. It can reach all the way up to the edge of the beryllium zone. It can propagate and excite higher conduction bands, so we'll have multiple band dynamics. However, at a certain point, this wave packet may photo-recombine, leading to the emission of attosecond pulses or the appearance of harmonics. Now, in previous experiment, we have realized how harmonic spectroscopy serves as a very sensitive probe of both dynamics and spatial information. Here, one can ask himself whether harmonic spectroscopy can serve as a very accurate probe of the band structure itself. So, in order to address this challenge, we have looked at harmonics produced from magnesium oxide, which is quite a simple crystal to consider. And here is a typical spectrum that we measure from this crystal. We see that the spectrum itself goes way above the first conduction band, which means that there are several conduction bands involved in this measurement. And then the spectrum itself looks completely different compared to the one we are familiar with in the gas phase case. So we do not observe here a flat plateau, but rather sharp spectral features which change dramatically as we rotate the crystal. See, to 30 degrees or 45 degrees, the spectrum itself changes quite dramatically. And for a long time, we ask ourselves, what is the origin of those bright spectral features and what is the information that they encode? Let's start by looking at the band structure of magnesium oxide. So this is the upper valence band and several conduction bands which are coupled to this valence band. And if I try to associate the brightest points in our spectrum to points within the band structure from which they are generated, then there is no clear conclusion that we can make. And then we realize that the proper quantity we should look at is not the band structure, but the difference between the conduction and the valence captured by the band gap. The band gap eventually dictates the energy of each harmonic order. And now if I try to make this comparison, then we can reach a very striking conclusion. We realize that each bright spectral feature directly maps into a critical point in the band gap, into a point where the gradient of the band gap becomes zero. So what is so unique about those points? Why do they lead to such high and sharp spectral enhancement? Let me go back to the kind of classical mechanism we have described before. This mechanism enables us to map or link different points in K-space into harmonic order by a set of strong field trajectories. At the band gap, at the critical point, we have not a single trajectory, but many trajectories, which all coalesce together, they interfere coherently to generate one huge constructive interference. At this point, in fact, we have a singularity in the mapping. And as in many other cases in nature, whenever we have singularity in the mapping, we observe the appearance of caustics. In our case, this is a spectral caustic, which is very similar in nature to the caustics that you would find on the surface of your coffee cup or the bottom of the swimming pool. So this is a very valuable information because we realize that the dominant part in our spectrum directly map the band structure itself. But this is static band structure. Can we take one step forward and look at the band structure as it is modified by the strong laser field? Can we resolve dynamical band structure features? In order to, again, address this challenge, let's look at the most sensitive point in our spectrum, and this is the point where harmonics are directly emitted from one of the energy gaps. So here are the two conduction bands in magnesium oxide, and harmonic 21, for example, is produced from within this gap, and therefore its signal is a bit suppressed. And now let me ask the question, what happens to this gap once we apply a strong laser field and increase the field intensity? Can we watch how this gap closes? Ideally, I would like to start this experiment by having some external knob that will enable us to tweak this gap. I would like this knob to slightly close or open this gap and then follow how the harmonic signal behaves. Unfortunately, I don't have such a knob, but what we can do instead is tweak the crystal so we can rotate it. This is the gap at 0 degrees. And as we rotate the crystal by only 20 degrees, the gap closes immediately and then changes quite dramatically. So with this simple manipulation, we achieve a very significant and dramatic switch between two dynamical regimes. In one regime, harmonics are emitted from the gap. In the other regime, it is emitted from the band. And these are two very different dynamical regimes. And the question is, how do we observe them? Well, we can follow how the harmonic signal changes. However, when we rotate the crystal, we change many other parameters as well. So we need a more accurate, more sensitive probe. And at this point, let me bring our favorite tool, the weak second harmonic field, which we add on top of the strong fundamental field. Again, this field is just a perturbation. It doesn't change the internal dynamics. In the atomic case, we have applied this field to slightly suppress or slightly enhance the atomic barrier. In this case, let's add the field to slightly close and open the gap. And as we change the two-color delay, what we induce are oscillations. So the harmonic would oscillate as we open and close the energy gap. And for each oscillation, we can extract an oscillation phase, which really serve as the most sensitive probe of such dynamics. And now I would extract this oscillation phase and follow how it varies when we rotate the crystal. So this is the oscillation phase at 0 degrees. And let's start and rotate the crystal. This phase changes slightly, and then all of a sudden dramatically drop by about pi radians and remain quite flat, which means that here we do not induce any change. And what we identify here is really the dramatic switch between the two dynamical regimes. A regime where harmonic are emitted from the gap into a regime when it is emitted from within the band. Okay, so now we have looked at static band structure. Let's increase the laser intensity and watch how this observation changes with the field intensity. So here is the same measurement with slightly higher field intensity. We see that already this jump becomes smaller and smaller and smaller until it becomes almost flat. In other words, as we increase the laser intensity, we lose our ability to clearly separate and distinguish between the two dynamical regimes. And careful theoretical calculation performed by the Max Born Institute in Berlin validate that what we have resolved here is laser-induced closing of the band gap between two adjacent conduction bands. So with that, let me conclude. Attosecond science was really born at the interface between ultrafast phenomena and strong field light-matter interaction. And building attosecond interferometry schemes enable us to extract the full phase information encoded in many such strong field phenomena and therefore reconstruct their evolution in time. And I think one interesting research direction to take in future would be to integrate attosecond with solid state physics, where there is a variety of phenomena that some of them have been predicted theoretically, but only few have been experimentally resolved, all the way from dynamical band structure through multi-electron dynamics or even subcycle phase transition. Thank you very much.
Thank you very much, Nirit, for very nice talk and very clear. I'm taking here, for the audience, if you have any questions, please write them down in the Q&A in the platform so I can pass them to Nirit, or Nirit can read them herself if she wants to. I don't see any comments or suggestions here. Okay, while any of you write down, I can start myself asking some questions, if I can. Okay, Nirit, when you were explaining about the tunneling times, okay, that you're measuring the tunneling times, but in the molecular case, at some point you were saying you do the interferometer and kind of the interferometer signal is that one of the different orientations of the molecule. So you say, okay, I'm mixing the trajectories that come from where the molecule was perpendicular, for instance, in your plot, and one linear. But my question is, how do you know which was the actual orientation? How is it actually working the experiment, Okay. I come from weak fields. So, for me, that's a different picture. So maybe I'm doing a very naive question, but just curious.
Yeah, sorry. So I didn't describe full experimental details. What we have used here are, we applied free field molecular alignment. So the way it works, and it's well established. We I think didn't bring anything new in that respect. We apply some impulsive excitation, which initiates molecular rotation. At a certain point, we stand at a revival where the pump field, so it's a pump probe experiment, the pump initiate the rotation, and then at the revival, one of the revival time of the alignment, we have an aligned ensemble of molecules, and here we perform the strong field interaction that leads to the emission of harmonics. And now you can change the polarization angle of the pump pulse, and by that you manipulate the angle of alignment.
Okay, but then in a given experiment, the molecule is aligned in a given direction.
Exactly.
You are not taking electrons from the parallel and the. Okay, then I misunderstood the plot.
Okay, so in a certain, maybe I was not clear. So in a certain experiment, there was only one alignment angle. Okay, but once this angle is, for example, rotated a little bit, then you have two tunneling events, but they do not exit from the similar orbital. For example, here it is exit at 90 degrees, here with the molecular axis. It's the same molecule, but the two direct, now I broke the symmetry.
Okay, yeah, okay, now I get it. So you do also a set of experiments for different alignments also.
Exactly. And then we repeat the same experiment as for different alignment angle, and we superimpose all experiments together.
And how many knobs, how many parameters are you really have to control? Let's say, because that was a linear molecule, but if you have, I don't know, a thetaedral or a more complex molecule,
then I admit that it becomes more and more difficult. This experiment works very nicely with simple and small molecular system where you need only one knob. With more, I think, complex molecular system, it becomes more challenging. Mostly what you need is to break the symmetry. So even if you do not achieve full alignment, even one knob enables you to break the symmetry. But of course, if you want to achieve higher degree of control, then more pump pulse have to be integrated. And there have been some demonstrations showing the ability to align more complex molecules. I admit that we didn't take it from this point.
Okay, yeah. Just curious if you were working still. Okay, I still don't see other questions. So I guess I'm going to take advantage to keep asking. Just a question, but this because I didn't work with solids. But For instance, I found interesting this work that you have in collaboration with the people of Berlin, where you see how the gap closes. What could be the practical consequences of saying I can control the closing of the gap? And indeed, it seems you can control it quite well, because I mean, if you control well the intensity of the induced laser that you put, you could even control quite well.
Exactly. So you can.
What would be some practical consequences of saying for that material, let's say, you know, or I mean, I know we are fundamental physics. I'm not asking nonsense. I'm just curious of if you know more about the topic.
Yeah. So I think this somehow reveals some very practical phenomena of pioneering experiment in the field. For example, I think two striking experiments, which I've described in my talk. One was achieved in the MPQ and many other groups in our community, showing how you can take an insulator and turn it into a conductor. If you are able to do that in a reversible manner, then you, in principle, achieve the fastest switch that works on a petahertz rate, and this will be really wonderful. I think what we have shown in our experiment is really the ability to fully visualize what happens to the band structure during this experiment. In magnesium oxide, you don't do much because you see the band closing between two conduction bands, but now I would take the same experimental scheme and apply it into other systems where the total electronic properties are modified, and this can be really wonderful.
Okay, thank you for your answers. Okay, I don't see if some people are not writing in the platform, or this is the problem of online. We don't know if there's some audience that are waiting for a question and not being able to connect. So, okay, don't see anything else. So maybe we want to close here. Otherwise, I feel I'm discussing along with you. I have to say you have quite an audience. I'm seeing almost 40 people. So it's not there. It's just not writing. So thank you again for the very nice talk. I really enjoyed it. It was very clear, very nicely shown. And to the rest of the audience, thank you for attending. Hope you enjoyed it. And hope to see you in the next seminar from the Attosecond network. And I don't know, Nirit, if you want to say anything else.
Just thank you for the invitation. It was my pleasure.
Okay, thank you.
Thank you.
Thank you all. So,
bye.
close the session. Ciao.
Ciao.
Ciao.